this class I will solve the question number 2 that was given in your midterm exams. So let me draw the circuit here, and thereafter we will discuss the procedure to solve this particular numerical. So in this particular numerical, it was tasked to find out this voltage V naught here, which is across this particular resistance. There are two methods through which you can solve this numerical. One is through the use of the mesh current analysis method, and the other one is through the node voltage method. So let us solve this using the mesh method. If you see in the mesh method, there are certain mesh available on which we have to apply the Kirchhoff's voltage law. However, if you closely look into these mesh, let me rename this one. Let us say this is I1, this is I2, this is I3, and this is I5. If we see here, then the mesh current I1 is passing through a current source, and therefore we do not need to write down the equation for this mesh. So I1 is simply equals to 2 times Ix, where Ix is the current flowing in this 2 kilo ohm branch, in this particular branch. So Ix, if we examine the direction of this Ix, then Ix is equal to I4 minus I5, and hence the value of I1 is equal to 2 times I4 minus I5. If we also see here, this I3 has a current source in its periphery, and therefore I3 is equal to minus 2 milliampere. Similarly, for this I5 we have the value equals to 4 milliampere. Now we are only left with two mesh, which is the mesh number I2 and we have mesh number I4 available. Both of them have a voltage controlled voltage source available. Therefore, it is quite interesting to find out using the only two equations. To find out what is the value of this Vx, Vx is the voltage in this particular direction across this 1 kilo ohm resistance. Because there are two currents which are associated with this voltage Vx, therefore Vx is equal to I5 minus I3, and because this I5 is known to be equal to 4 milliampere and this I3 is minus 2 milliampere, so this becomes equal to, so Vx is equal to 6 and that is multiplied by 1k, so that is equal to 6 volt. So now we have the value of this voltage source as well, which is equal to 12 volt. So let me write down the equation for this mesh current I2. So that is equal to 2k I2 minus I1 plus 1k into I2 minus I3 minus 2Vx, that is equal to 0. So if I further expand this particular equation, then that is equal to 12, and if I solve this and I substitute the value of the I1 in here, which is this thing 2 times Ix, and after substituting the value of Ix, this I1 is based on the mesh current number 4 and mesh current number 5, out of which mesh current number 5 is also known. So if I substitute these things, I will end up this particular equation at 3k I2 minus 4k I4, that is equal to minus 6, and this is my equation number A. To write down the equation for mesh number 4, so let us write the equation for mesh number 4. So the equation for mesh number 4 is 1k into I4 minus I1 plus 12 plus 2k into I4 minus I5 and that is equal to 0. This can be written as 3k into I4 minus 1k 2 into I4 minus I5, that is equal to minus 12 plus 2k into 4 milliampere, because we do know what is the value of the current I5. And if we play with this particular equation and also we end up at a value that I4 is equal to minus 12 milliampere, and that gives me equation number B here. Now because we have this I4 available, so I can get the value of I1, which was 2 times I4 minus I5, because I1 is associated with the current control current source, which is here 2 times Ix, and Ix is the current which is flowing in the branch which is common between the mesh current number 4 and mesh current number 5, and therefore this I1 equals to 2 into I4 minus I5, and this gives me minus 32 milliampere. Now that I do know what is the current I1 and what is the current I4, I can get the value of this V naught, where this V naught is equal to I1 minus I4 into 1k, with the values of I1 and I4 substituted in this particular expression. I get the value equals to minus 20 volt, and that solves for this particular numerical using the mesh current analysis method. We can also solve this method by going after the node voltage method. However, the node voltage method will yield more number of equations compared to this mesh current analysis method. For example, if I say that this is one mesh, this is one node, and they are actually being made in one equation using the concept of super node method, but I do require the voltage at this node and at this node as well. So in a nutshell, if I opt for this particular method, then I must say that I need to know the voltage at V1, V2, V3 and V4 if I consider that this particular node is actually a ground or a reference node. And thereafter, because we can create one super node here across this 2Vx, and that will make the total required number of equations for a node voltage method equal to 3. Remember that in the mesh current analysis method, we require to solve only for these two equations. However, if we move on to the node voltage method, the total number of equations that are required to solve are equal to 3 if we go for the super node method between this node V1 and V2. Let me first copy this diagram here. So now that we have this circuit available, let us apply the super node on the nodes V1 and V2, because there is a voltage source which is common between those two things. So using the super node, we get V1 over 1k for this branch. Then we have V1 minus V4 over 2k, then plus V2 over 2k. Then I will write V2 minus V4 over 1k plus V2 minus V3 over 1k, that is equal to 0. So this is 3 times V1 plus 5 V2 minus 2 V3 minus 3 V4, and that is equal to 0. Also, you should notice here that because of this constraint of this dependent voltage source we have, so V1 minus V2 is equal to 2 times Vx, where Vx is the voltage between this node V2 and V3. So Vx is equal to V2 minus V3. So we have V1 minus V2 is equal to V1 minus V2 is equal to 2 times V2 minus 2 times V3, and this gives me V1 minus 3 V2 plus 2 V3, that is equal to 0. Now I will write down the node voltage equation for node number 3. So going after this node number 3, so we have two currents associated here. So this gives me V3 minus V2 over 1K plus 4 milliampere plus 2 milliampere, and that is equal to 0. And this gives me that V2 is equal to V3 plus 6. So I have got equation 1 here and another equation here. So now if I write down the KCL for node number 4, then I get V4 minus V1 over 2K. Then I have V4 minus V2 over 1K, then minus 2 milliampere minus 2 Ix, and that is equal to 0. Also notice here, what is this Ix here? For this particular case, Ix is equal to V2 over 2K. So now I have these three equations available. So if I substitute this value of Ix into this particular equation, then I get minus V1 minus 4 times V2 plus 3 times V4 minus 4, that is equal to 0. And this gives me 3 times V1 plus 5 times V2 minus 2 times V3 minus 3 times V4 is equal to 0. And therefore, V1 minus 3 V2 plus 2 V3, and that is equal to 0. So this implies that V2 is equal to V3 plus 6, and minus V1 minus 4 V2 plus 3 V4 is equal to 4 using this particular equation. So this implies that V1 is equal to 18 plus V3. So if I now put in the value of this V3 here, then I get 3 into 18 plus V3 plus 5 into V3 plus 6 minus 2 V3 minus 3 V4, and that is equal to 0. So I have actually substituted this value into this equation, and thereafter this equation becomes this equation. So we have 6 V3 minus 3 V4 is equal to minus 84, and this gives me 2 V3 plus 28, that is equal to VA. So V3 becomes equal to minus 38 volt, and therefore V1 is equal to 18 plus minus 38, and this gives me minus 20 volt, which is exactly the same as we solved for the mesh current analysis method above. But notice here that the amount of complexity involved in undergoing with this particular numerical using the node voltage method is more than the complexity we have seen for opting the mesh current analysis method. So I hope that you have now understood this particular numerical. It was also very straightaway simple numerical. So I hope now the things are quite clear. Regarding the question number 3, the things are a little bit complex here, because this question isn't a very simple numerical, as you can see here. However, if you apply some of the instincts of your basic circuit analysis that you have developed so far, the things becomes a little bit easier. So we were tasked to find out the value of this RL such that the maximum power is transferred to this particular load. This requires finding the Thevenin equivalent of this circuit on these 2 points A and B. Remember that this was 2VA, where VA is the voltage across this resistance of 8 ohm. And we have 3IA here, where IA is the current flowing through this particular branch. There was a 9 volt here. To solve for this thing, you require to find out the VAB or the VOC or the VThevenin at terminal number A and terminal number B. And the second thing is to find out the I short circuit between point A and point number B, right? So to solve for this particular numerical, we first need to remove the RL from the system and redraw the circuit. So if I redraw this particular circuit, it is quite easy to remove this resistance from these 2 points. So now I am available with this A and B here. So let us first of all see that if we have this 3IA entering in this node A and 1 ampere 1A or single IA is leaving through this branch, then 2IA is the current that shall flow through this 8 ohm resistance. Also notice here that this 2 ampere current is flowing through this 2 ohm resistance, and therefore this 2 ohm resistance has a voltage drop of 4 volt across itself. Also this 2 ampere current source is entering here, so it is producing 8 volt across this 4 ohm resistance. And if I apply the Kirchhoff's current law at this particular node, then IA is entering here, and here we have 2 ampere current entering here. So the total amount of current which is entering this 2 ohm resistance is IA plus 2, right? And therefore I have now gathered enough of the information here. So let us solve this particular numerical to find out what is the VOC. So to find out the VOC, VA, which is this voltage, this VA is equal to 8 into 2 IA, and that is equal to 16 IA. So once I know what is the value of this IA, I can easily find out what is the voltage VA here. So in loop 1, let us say this is the loop 1 here. So applying the KVL in this loop 1, let us say this is loop 1. So we have 2 times IA plus 2. Then the same current is entering through is flowing through this 1 ohm resistance. So this is 1 times IA plus 2 minus 16 IA, which is the voltage here. So I have directly substituted the value here, minus 2 VA, that is equal to 0. And if I expand this particular equation, I get 2 times IA plus 4 plus IA plus 6 minus 48 IA, that is equal to 0. And this gives me the value of IA to be equal to 0.134 ampere, right? Now I have calculated the value of this IA. Now that this IA is known, I can calculate what is the voltage drop across this 8 ohm resistance. So if I apply the concept of finding the voltage between the 2 points using the Kirchhoff's voltage law, then I have to follow this particular path, because KVL can be applied on any path. Let us say this is VAB, and this side plus and this is negative. So applying the Kirchhoff's voltage law at A, let us say this is B, this point is B, let us say this is C, and this is D. So let us apply on A, B, C, D, A. Let us apply the Kirchhoff's voltage law here, and this gives me AB is equal to 16 times IA plus 9 plus 4, and that is equal to 15.4 volt, and this is the VOC or the VThevenin of this given circuit. So we have calculated the VThevenin, half of the circuit is solved. To solve this particular numerical, we shall have to create a short circuit path here. Now once I have created the short circuit path here, I can write down different equations here as well. So now if you see, there are 4 mesh available. Let us say this is I1, this is I2, this is I3, and this is I4. Between this I3 and I4, we create a super mesh. We create a super mesh here. And for this I2, the value is known because we have a current source here, and that I2 is minus 2 ampere. Also, we should notice here that I4 minus I3 is equal to 3 times IA, and IA is the current which is flowing here, which is this current. So IA is equal to I2 minus I1, and therefore I4 is equal to I3 minus 6 minus 3 I1, and let us say this is our equation number A. Now we will create a super mesh here, super mesh between I3 and I4. So this provides us a value that is equal to minus 9 plus 8 I3 minus 8 I1 plus 2 I4, that is equal to 0. Let us say this is equation number B here. Also we will apply the KVL in mesh number 1. So by doing so, we get 3 I1 plus 16 into I1 minus I3 plus 8 into I1 minus I3, that is equal to 0, and this gives me I1 equals to 8 by 9 I3, or it is equal to 0.88 I3. Let us say this is equation number C. Now if I substitute C in equation number B, we get 8 I3 minus 8 into 8 by 9 I3 plus 2 I4, that is equal to 9, and let us say this is equation number D. Substitute equation number A into equation number C, right? So, and solving for the value of I4, we get I4 equals to 8.32 ampere, and this gives me ISC, that is equal to I4 minus I2, and that is equal to 10.32 ampere. So now that the ISC is known, R Thevenin is equal to VOC over ISC, and that is equal to 1.47 ohm. To find out the power which is delivered to this load resistance, so we need to divide this V Thevenin square divided by RL, and therefore the power is equal to 38.93 watt, and this provides us the answer for this complex numerical. Remember that the numericals containing the maximum power transfer theorem are always complex, no matter how simple they looks like at first sight. There are dependent sources available, then the circuit requires not only the critical thinking, but also appropriately putting down the equations in a very sequential manner to solve for a given circuit. So that's all for the midterm solution. I hope that now you will understand that the midterm exam was a little bit trickier than I actually used to give to your earlier classes. So see you then in the next class. Take care. Thank you very much.